Hello everybody, my name's Ash. The purpose of this talk is to try and help free flyers get a broader understanding of basic weather. I guess we all tend to get a bit too focused on the numbers on our weather apps and zoom in and look at the wind speed and direction that is forecast and the thermal strength, even the star rating or whatever, without really understanding why they're suggesting these different figures, and or even joining the dots and working out why it was windy yesterday or why the cloud base is so low today or whatever. And I think a general talk like this might help to pull those pieces together and help us understand it. Earthrise from Apollo 8. Well, this was taken on Christmas Eve 1968. It was just one of the first pictures anyone had ever seen of the Earth from space. And I was a child of 9 and I was absolutely spellbound. I think we see these photos all the time nowadays, so it's become old hat. But back then, it really caused a shift in my 9-year-old perspective. And I think many humans at that time were suddenly aware that we'd all been focused on the little things and not really realised the bigger picture. We were sort of all inhabiting this beautiful, amazing iridescent globe hanging in space, and don't be too romantic about it, but I think it really made me think about how easy it is to just get so focused on little things you don't even see the bigger picture, and the bigger picture is absolutely essential for understanding anything. So I think this talk is really mainly to try and clarify some things, but also to try and rekindle a childlike awe that I definitely had back then, and to if nothing else, enjoy this wonderful phenomenon that we call the weather. I'm going to talk about global weather patterns and then sort of like zoom in a bit more to more local stuff, and I finally end with a couple of applications that would be relevant to us here in Derbyshire. I want to tell you that I'm no expert and I'm just an enthusiastic amateur. Right, the atmosphere, the atmosphere, is a wonderful mix of mostly nitrogen but a bit of oxygen and CO2. That is actually a perfect mix for life. Gives us all that we need. Well, it doesn't give us one thing that we really all need for life, and that is water. But it easily absorbs moisture and deposits it. It's got this wonderful system we all learnt about called the water cycle, where water is very readily absorbed by the atmosphere from the sea, and billions of gallons of it can be transported thousands of miles and deposited on the dry land, enabling that land to grow vegetables and plants and provide cover for the animal. Anyway, I won't go on too much about that, but it's wonderful. The atmosphere is really quite thin, and I think it's surprisingly thin compared to all the pictures you see in the diagrams in the books. But even if you take it as 100 kilometres, which is a common distance to give, it's still only about the thickness of a coat of varnish on a cricket ball, and it's surprising really. But even at 100 kilometres, it's very rarefied out at the edges. It's worth bearing in mind that, like, really 50% of all the gas in the atmosphere is contained in the first 5.5 kilometres, about 18,000 feet. Analogies. I'm going to try and use few words and as many pictures as possible, and I'm just giving a kind of a warning or a heads up that I'm going to use pictures and examples from everyday life to try and describe the atmosphere and understand it, get a handle on it. But analogies are never perfect, of course, just like this one isn't, and so I've got to bear in mind myself that they don't suit everybody. They're not supposed to be taken absolutely literally. They're supposed to be little handles, maybe see them as sort of stepping stones, not the final picture. Right, okay, well, this is a great big solar energy machine. The whole Earth runs on it, incredibly large quantities of it, and the sun's rays that hit the Earth, we see it as sunshine, so it's all visible to us, and heats up the Earth, loses quite a bit on the way down through the atmosphere, some reflected, some absorbed, quite a bit absorbed by the ozone. I might talk about that in a bit, ozone layer. But anyway, down near us, the clouds have a reflecting effect on it as well. So that's worth bearing in mind, although it's never as much as we think. I think it's amazing how much solar energy penetrates cloud unless it's particularly thick. At night, there's an equal amount of outgoing energy. This is invisible, so it's longer waves, so it's not in our visible spectrum, but just as much heat is leaving the surface as it gained during the day. Long wave means that it's affected by different chemicals and gases in the atmosphere. Greenhouse gases really help to stop the fluctuations between hot and cold being too extreme, which is helpful for life, so nights don't get too cold and the days don't get too hot. Cloud again reflects quite a lot of this long wave radiation back to the Earth. As we kind of know, if we've ever been out on a clear night, it's often a lot colder than it would have been when it was cloudy the night before or whatever. So we can feel the difference cloud cover has on the long wave radiation. Right, well, how do we all know about the atmosphere? Only 150 years ago, I think this is amazing. People knew about the weather. They definitely had all the instruments as well. There's various instruments here that were quite accurate. Hundreds of years ago, we had fairly accurate barometers being invented, I think the 1600s or something. And they knew things like if the barometer started falling in its reading, going to lower pressure, that we were in for unsettled and stormy weather. That was really, really well known and understood hundreds of years ago. So they could draw synoptics to show roughly where the pressure was. So in some ways they were really good. They were probably better than us. This is one of the things I wanted to drive home, is that
people without any ability at all to sample the air at altitude
worked out a lot of things by just watching how weather develops. And the professionals in their day were really kind of farmers, and particularly sailors. This country's had a lot of sailors, and their livelihoods and their lives depended on a good understanding of weather. So they got really clued up and looked out for patterns and signals that they could pick up on to know when it's going to be windy and what parts were going to be likely to be stormy and all that kind of thing. They were really into it, and I think that we've got much more information and yet a little bit less awareness, and I'm hoping that we can just try and get a bit more aware of things we should have picked up on. But this all changed. What really changed is technology. So what's happened in the last mainly 100 years really, we've had a fantastic growth in technology we could have only dreamed about hundreds of years ago. Flight, obviously, that was the main one. Powered flight, and especially pressurized cabins since the sort of 50s, which means that planes could get really high in the sky. But the weather balloons were developed around the 1920s
to collect atmospheric data.
Around the same time as Germany was really getting into gliding. Europe had been a bit upset with how Germany had been in the First World War and had some sort of treaty called the Treaty of Versailles, which limited the development of powered aircraft but let them have as many gliding clubs as they liked, and so lots of young men took up gliding. I love this guy Günther Grünhoff. I've mentioned him before. A bit of a hero of mine, a bit of a nutter, who, for the sake of meteorology, took instruments up and flew them wherever the meteorologist wanted him to go, which was normally into the middle of a big QNIM, and bring back the readings. And there's fantastic stories back there in the late 20s of some of these pilots, and many died. It was a tragic time, but very exciting. More recently, of course, in the last sort of 50 years, we've had just increasing amount of satellites that give us really up-to-date, almost real-time images of weather patterns all over the whole Earth. Amazing. Different kinds of satellites at different altitudes, but all feeding back vital information. And computing. Computing is the biggest thing. I just want to not spend too much time on it, but we hear about it all the time, and computer modelling, like numerical atmospheric modelling, is taking over, and it will increasingly just dominate more than we think. Computers are going to become
the primary source
we're going to have for weather, but it's mainly because we've had an increase in computing speed that's been happening every 2 years. Computer processing power doubles and the chips get cheaper, so it's become possible to do what we couldn't even think of doing only 10 years ago in terms of fine scale resolution of the whole Earth in 3D and get a computer to process it. See these charts here? These are all computer models that cover the UK. Probably not all of them, but as many as I could find. quite a few of them global, and then quite a lot of more local European ones that can have finer resolution without exhausting their computer power, because they're only covering a certain country. Like Met Office have one for the UK, very high resolution model, but if they tried to do that kind of resolution for the whole world, the computer would take many hours to process the data. This is a graphical description of how a computer takes information, the latest information if possible, from satellites, weather balloons, and also increasingly from civil aircraft like airliners that transmit virtually live data of the conditions where they fly. And that information is very unevenly spread over the whole Earth. So one of the things a computer needs to do is to assimilate it, is turn it into a grid, and then once they've got that grid, they have to run great big simulation of what would happen if, and they have these whole things called ensembles. You know, I won't go into the detail too much of computer modelling, but it's really the way it's going to be. Just bear in mind that don't always go for the higher resolution, because higher resolution models of any type take much longer to process, so have to use more out-of-date initial information. So although they're better, at certain things they're worse, and some aspects of weather really benefit from high resolution models, and one of them is actually surface winds. So if we want to have a really accurate surface wind forecast, it really helps to have high resolution models. Satellite imagery, this is from geostationary satellites over 2 months, January and February I think it is. Well, the orange signifies rainfall. Look how the rainfall is constantly lashing the UK. Isn't that amazing, isn't it? Pretty constant. But this is not a very high resolution image, and they do better ones. So they've got one, I think it's got one coming up, which will show this is using mostly polar orbiting rather than geostationary ones that go around once 24 hours and are really high in the sky, 22,000 miles up. The orbiting ones take a slice, go around every 100 minutes or so, very low, 300 to 500 miles or so, and get really fine images. But anyway, notice how the swirls and lines of rain go in an anti-clockwise direction in the northern hemisphere and a clockwise direction in the southern hemisphere. What's all that about? See out in the middle along the equator, it looks very different. It just has its sort of splatters, whereas north or south it's going long, thin, squirrely lines. What's all that about? Air masses. These are very large regions of air which have slightly different qualities in terms of temperature normally and humidity, and of course they vary depending on where they originate in temperature. So if they come from the poles, they like to be a lot colder than the ones that originate near the equator. And also bear in mind that an air mass passing over an ocean will pick up a lot more humidity from the ocean, particularly if the air mass itself is warm, whereas air passing over land usually remains quite a lot drier. So air masses swirl around the whole planet in the lower part of the atmosphere that we call the troposphere, and they can be as big as a continent, and any difference in temperature between two air masses creates weather at that boundary, and we call that boundary a front. So whenever you've got slightly warmer and slightly colder air masses coming together, you'll get the cold cutting underneath the warm and the warm riding over the top of the cold. It's just an inevitable part of two air masses of different temperatures coming together. And if the cold air is dominating and pushing into the warm, it's called a cold front. That's the first image there. These travel quite fast, quite often about 30 miles an hour, and travel quite quickly and have quite a steep kind of snowplow effect. And on the synoptics, they've got these sharp teeth, and not always blue, especially in the black and white diagrams, they're not blue. And the actual snowplow effect is quite steep. So this line, if you see this line, you nearly always associate it with quite a narrow band of quite heavy rain. And here's a warm front. If the warm air is dominating and pushing against the cold air mass, then it creates a slightly different effect. The warm air is riding over the cold. The drag of the earth stops it, and the warm air rides over the cold, and it creates a very shallow wedge. And that generally means we get weather that's, you might get it's quite a lot of cloud, but also just like drizzle all afternoon or something, if we get a warm front like this. And it's got very blunt teeth, and it's red if you've got a coloured diagram normally. The next image, the third image, is just a stationary front, which tends to be halfway between a cold and a warm front in its characteristics. They don't often show these, so you do sometimes notice a warm front is basically stopped, and then the next minute they're showing it as a cold front because it's starting to move the other way, and when it moves the other way it starts to develop the characteristic of the other front. The occlusions, they're very common. So if it's a very deep low and it's been around for quite a while, and then there's a spiral effect, I'll talk about it in a minute, where the cold, because it goes about twice the speed of the warm, catches up with the warm, and what happens is it's kind of effectively pinching the warm sector completely off the ground. Again, I'll talk about it later, but it's quite an interesting thing to notice. Vertical structure again, I just want to quickly talk about that all this frontal stuff that we've been talking about basically relates to the troposphere. That lower section there, up the side here we've got the altitude in kilometres, and on the bottom we've got temperature, and you can see that the troposphere has got a very steady decrease of temperature generally with height. And then you get to the next bit up there above it, which is the stratosphere, where the reverse happens, where the temperature actually increases again with height, then drops again in the mesosphere, and then as we get out into space, the thermosphere, it goes increasingly higher temperature as we get to less and less molecules. See the picture on the left, it shows the various layers again. See how it's varying in thickness. There's a kind of a squishy effect. Yes, it's definitely not to scale. Right, so there, see how the boundary is not even, and now that's just a diagram, but it makes a really big point that the atmosphere is not constant thickness, because it moves around and has eddies, and it's very much like the ocean. It's probably the nearest image I can think of. It's got waves and all sorts of things going on. Here's a simple cross section of the atmosphere. Where the atmosphere is thickest on the surface, we record that as high pressure region. Where the atmosphere is at its thinnest, it's just basically because there's less air above us. The column of air is less heavy in the low. And notice the circulation as well. So we've got, as we've got this high here, we've definitely got a general migration of surface winds towards the low. It is spiraling, we'll talk about that in a bit. So it's not direct, but that's basically the circulation is from high to low. And then we also need to bear in mind that in the low, the air is characteristically rising in a low, and in a high, the air is characteristically descending. So this creates this kind of quite predictable flow. Where of these A, B and C and D would you expect to find the least cloud? Right, well, yes, it would definitely be about A. High pressure nearly always signifies less cloud, and low pressure would be the reverse. There's more cloud present in low pressure. Look at this. This is an animation. This is taken at 60 kilometres up, so it's very, very high up there in the mesosphere, and shows vertical movement of the atmosphere. The top of the scale is 90 metres per second vertical up, and the bottom of the scale, the black, shows a descent of 100 metres per second. That is absolutely huge. Play it again. Look at that. It's just incredible, I think, and helps us to understand that here's where the highs and lows are going to turn up and hugely impact our weather all the time. It's 800 times less dense, but it's a lot like water. But even if you just get a stream like this, when you put your finger in, look at what a funny thing that happens here. Look, see the ripples. Even when you haven't got your finger in, there's kind of rippling happening. But when you put your finger in, did you notice? I'm going to try and play that again. Just notice how water, very similar to the atmosphere, loves to ripple. In fact, look how the ripples go upstream of the interference, the finger. and forms a very fixed frequency, like it wants to resonate at that frequency. And I think that's a very important thing to try and understand about
The upper atmosphere.
is that it likes to ripple. Right, what about all the swirling though? We get quite a lot of swirling going along. Why is everything going round and round in like a spiral, like Catherine wheels? I think it's quite important to understand this thing called Coriolis effect, but it is hard to find a nice, homely example. It probably needs to be a little bit better than a coffee cup, unless you start to try and imagine a coffee cup that is as big as the Earth, and that it's spinning once a day or something, and that you're sticking your spoon in to indicate some sort of drag on the. But again, it's not very realistic. But you do get similar patterns, but it's probably too dissimilar to be a useful guide. Better probably to just run this short clip of that's by the Pilot Institute, which just shows it. The best example is this roundabout idea, where the two people one kicks the ball to the other in a straight line, but because the roundabout is rotating, from their perspective, the ball seems to do a curve, and really it did go in a straight line. And this affects how air flows on the planet. The whole atmosphere is affected deeply by this. Another coffee. Sorry, I'm using coffee this time to try and show how if you stir really vigorously, you can create a low in your coffee.
And this is similar to what happens in the atmosphere, where there's a low and the air spins around it.
And here's a wonderful example of, this is taken from the International Space Station,
Of Hurricane Florence in 2018.
Right, this is a really important diagram and shows how the winds tend to flow around the planet. Got these different flows that are quite reliable. So they vary, but they are quite reliable, the patterns, and even these circulatory patterns here that they call Hadley cells. Right, so notice that over the equator we tend to have a regular low forming over the equator, and so we've got airflow tending to go upwards, as we heard earlier about the lows tend to mean we've got upward rising air characteristically, and this big flow happens and then comes down where we've got this subtropical high. So these are called the horse latitudes because they traditionally, when sailors were reliant completely on sail, they got becalmed at the 30-degree latitude quite often. There's no real significant weather or wind happening, and they were called the horse latitudes because if they were stranded for long enough, they would be worried about surviving, and they would throw out the horses because so that they had enough water and provisions and food for the humans on board. Right, here's a feral cell, and here's another line of demarcation, the 60-degree line, where we get another low, and it's a boundary between the warmer air and the very cold polar air over the North Pole, and that boundary is what we call a polar front, and it divides the polar cold air from that warmer
Temperate
air in the sort of mid latitudes. The thickness of the atmosphere is definitely thicker at the equator than it is at the poles. Anybody got any ideas why? Well, it's not because of centrifugal force, which is what some people have said, but it's to do with the fact that the air is so much denser at the poles. So it's basically the temperature difference. Right, that polar front that we're talking about, this is a bit of a simplistic diagram, again, please forgive me, of the polar front, and showing the cold, particularly cold air mass that tends to sit over the pole. It doesn't look as straight as this, the line, never. It wiggles quite a lot, and it passes very close to the UK. Notice it just clips Scotland. At high altitude above it, we have what we call the polar jet stream, a strong flow of air from west to east that follows that line wherever it goes, really, the boundary. If the polar front is to the south of the UK, we will be in the cold polar air mass, and if it is to the north of us, we'll be in the warmer temperate air mass, and that makes a big difference to our weather. So the meteorologists are always talking about the jet stream has moved to show whether we're sort of under it or over it. Right, here's a nice diagram showing how the polar front, when it's stable, looks like this, not moving much. See, it's a stationary front, but the Coriolis effect and the tendency that's exaggerated if ever you get a low pressure region passing over the polar front. You get a twisting action, you get this kind of rotation start to happen. It's almost like a bite is being taken out as the low passes over, and the twisting starts. And we were saying earlier about how cold fronts tend to advance more quickly over the surface than warm. So we get this kind of thing happening that quickly turns into a swirl where the cold is actually catching the warm, and what we call the warm sector here is actually getting squished, and the cold sector is becoming more dominant, so it's all cold all around the top. See the green bit? This is where rainfall is likely to happen in this kind of situation, and this is really typical, and we get it a lot. Well, we get into the middle of a lot of these because we're right on the polar front. But notice how as the system further develops here at E, we've got an occlusion happening where the warm sector has now been pinched completely off the surface, and once this occlusion has finished developing, the low tends to split away completely from the original front. But having told you how simple it is, this is a kind of where we've got a really intense low over a few days over the polar front. It's twisted it so much that it's far from simple. The diagrams become really deeply complicated, and there's lots of occlusions here where the cold has caught up the warm and lifted a layer, and then we've got multiple lifted layers, and we don't show it. The meteorologists tend to only show fronts that have actual weather associated with it, or else you'd have, this would be much more of a dartboard than it actually is right now. Right, back to the whole atmosphere again just for a minute, just to show you that there's one bit of the atmosphere that matters more than anything, and the troposphere is definitely where all the weather happens and where all these fronts and everything occur, and how these upper layers do quite an important job of protecting us from harm, but also very active in creating ripples. So, but this bottom layer, I want to zoom in on that and just show you that there's a bit below that, only part of the troposphere right at the bottom, that's really significant for us. It's the bit we fly in and live and breathe in generally. What do we call it, do you think? Yep, the boundary layer, or the convective boundary layer as it's often called. It's just really, really important. It's only about 5,000 or 6,000 feet max, probably in summer normally, and drops of basically nothing at winter and overnight. The CBL is, well, this is just taken from Jean Norberson. We used to call him Jean Oberson, I think, because we never knew that he was French. But he's got some wonderful documents I might share with you. And this is snatched straight from one of his documents on the CBL. But it's the bit that's in contact with the ground, and it's quite unique. It's very different to the rest of the atmosphere in that its convection has made it really homogeneous, and the diurnal, the day and night cycle ensures that this layer gets very, very mixed. It behaves very differently to the rest of the atmosphere. It relies very heavily on basically what we call ideal gas laws. Again, this might befuddle some of you, and I really don't want to befuddle anybody, but it also might be appreciated by those of you that are a bit more scientific. That, as I said before about weather models, they rely very much on this understanding that the ideal gas laws present, which is that the pressure, the temperature, humidity and density, all these characteristics, they're all interchangeable, so they all affect each other. So for instance, if one goes up, the other goes down, and you cannot change one without another changing. So I've got a question. If we reduce the pressure of a parcel of air somehow, let's say we lift it by 300 feet or something, reduce the pressure of air of a parcel, what would happen to the parcel's temperature, density and humidity? Yeah? Yes, it would become cooler and less dense. What else? It would also have high relative humidity. So if it was near to being fully saturated, it might turn into cloud if we lifted it at all. Anyway, here's a more practical example. In this room right now, there is convection happening. Circulation is going on around the room as we speak. Warm air rising, expanding, and then contracting and cooling and becoming more dense and going in a nice circle, presuming that the radiator's to one side. But what if we do something now? What if we were to move the heater from the side? Oh, I was going to ask you where you'd put your socks to dry them, because that's quite important. I think to just understand evaporation and stuff like that, it's helpful to just, I think we know the answer, but it's sort of helpful to think about where we would get the most drying and where we would get the least drying in the room. And it definitely would be less in the bottom right hand corner of this diagram, where the air would be much more humid and colder, and both those features affect the ability of your socks to dry out. Right, as I was saying, say we want to move the heater from its position and stick it to the ceiling. Now, what would happen? What would happen to this circulation? We had a nice circulation going on, absolutely no circulation. It would heat up that bit, but there's no temptation for either the warm air to mix with the cold or the cold to mix with the warm. Whereas before, there was a constant mixing going on. Here's a really fun experiment you can do, using hot water and cold water in glasses, with the hot water coloured red and the cold water coloured blue. And we can put the hot glass on top of the blue cold glass with a bit of plastic between them, and then pull out the plastic and just see if there's any movement between the two layers. Right, look how little movement there is. The boundary stays really distinct, and there's absolutely nothing happening between the two layers. They're just staying unmixed. Right, if we do the same with the two cups, but this time reverse them so that we've got the cold one sitting on top. What do we expect to happen now? Any difference? Just got to move the plastic away without spilling all the water everywhere. And look at that. Incredibly different to the first experiment. So we could just put cold air on the bottom. So we could put, maybe chuck a load of snow in the room across the surface there. Forget the heater at the top, and we've just cooled the lower bit rather than heated the top bit. We get the same effect. No mixing. There's no desire for either layer to swap places, and they just remain really separate. In reality, we do get a tiny bit of mixing in the boundary between the two layers, a very thin bit. We call it an entrainment layer. But now I want to suggest that this is what it's like outside in the real world, on a big scale, because we had that long wave radiation, making the ground cool. Overnight, we've got this stable boundary layer, the bit that's in contact with the surface, but this boundary offers very little drag, and so you can get strong wind up here, and we wouldn't know it. It doesn't really matter during the summer months, it doesn't really matter, but it does affect us quite a lot in winter, where we get the same thing, like a stable boundary layer that's even thicker and more stable and doesn't really get broken up during the day. And we still get this kind of lamination happening, where there's a warmer air mass above and a colder air below, because the heat's being lost to space during the night in the same way it would during the summer. But this time we haven't got a nice mixing layer that's caused by the thermals and by air being heated from below. So we get this kind of problem in winter, where we're in direct sort of contact really with the upper atmosphere, which, as we know, ripples all the time if it gets half a chance. And that previous shot was taken by Richie Carter on that same day, on the 22nd December, and this one's taken by me. That's roughly what the rasp sounding looked like. But it helps you to see how it forms and how wonderfully laminar that is once you're up there. But one of the problems we often have in these kind of winter conditions is that we've got no wind at all to talk of in the the nocturnal boundary layer. It's only a couple of 100 feet thick normally, and then all of a sudden you get into the stronger wind, the meteor wind, and where that interface happens, where that point is, where the two air masses slide over each other, you get turbulence, and it's quite dangerous. Another thing that's really interesting about the convective boundary, the nocturnal boundary layer, is that it becomes quite dense, and so it tends to pool and flow into the lower, into the valleys, off the high ground, and certainly off the peaks. And so we get this tendency for it to flow slowly overnight to gradually fill in the low ground and pour off the high ground. And that makes a significant difference on a normal thermic day. When the sun first comes up and starts to heat the hills and heat the whole surface of the ground beneath, that where there's a thick nocturnal boundary layer still present in the valleys, it takes a long time for thermals to really start to kick off. We get them sort of starting, pushing it up, but it'll actually bleed in this situation, which is supposed to signify something like Bradwell. It'll bleed and it will actually flow up, so we get lovely thermals maybe on top of the hill, even though out in the valley there's actually no thermals getting through the nocturnal boundary layer yet, because the sun hasn't heated it up enough to destroy that boundary layer. And so we can actually leave the hill sometimes thinking, right, this is flipping good, we've got 3.5 grand climb, that's brilliant, and then we head out of the peaks, and as we leave the Peak District we've now gone into the flatlands, and all of a sudden the thermals are really weak and it's hard to stay up. And this might be quite a good explanation for where people feel that the descending air put them down. Maybe this is a better explanation. Anyway, here's a nice picture of Hope Cement Works in the morning, 6 o'clock in the morning, and this showed a Nottingham trace, sounding trace around that time, and shows how deep. Can you see the how the dew point? I'm doing it again. I'm talking too much about tephograms. I promise I'll try not to. But yeah, just briefly, wherever the dew point line touches the temperature line, we've got sort of like 100% humidity, so we're very likely to get fog. And the thing about fog is that it actually reflects as well. So if we got overnight fog, we tend to get a delay in the solar radiation getting through to the ground because it's reflected by the fog, so it delays the onset of convective circulation, which will get the convective boundary layer up and running and allow us to go off on XC. We need the temperature to be something more like 13 or 14 degrees on this particular example, before that's the surface temperature, before we can expect this inversion to get broken and for the normal day to start to develop, but maybe even 20 degrees before it really starts to get decent. And it's very similar to what happens when you get overnight rain. Overnight rain will mean that the surface will be wet, and so when the sun starts to shine, it will be only evaporating the moisture off the soil, not heating the surface. So that energy is being spent on evaporation rather than heating, so we get quite a definite delay. I've noticed a lot, or even not really a decent thermic day after all, because the ground was so wet overnight. And I think that RASP and other models don't seem able at the moment to take this into account. So I've noticed quite a lot that if we've had overnight rainfall, RASP hasn't really picked up on that at all, and yet it will definitely not necessarily spoil the whole day, but delay the onset of a good XC day by maybe a couple of hours as the water takes time to evaporate. This is just a really useful site. Just wanted to throw this in before we finish, that we've often struggled to know this kind of danger of when, especially in winter really, when you zoom in on a scooty, they don't really, there's not enough detail to show you exactly how windy it will be at what altitude. So it's really useful to have Neil Charles's site, wind at altitude. There's a very good example of a really dangerous, like you could be tempted if you're at Bradwell takeoff and it's only showing sort of 19 or 20, you might think, well, it's not too bad. And this is definitely a winter profile. You'd never normally get this gradient in the summer because of the convective boundary layer mixing it up and kind of protecting us from any real sudden strong shears. But in the winter you can get violent shears where it suddenly picks up, doubles in just 10 meters or something, and it obviously makes chaotic air, which is really not good news for paragliders particularly. Right, this is called a boundary layer diurnal cycle, and this particular one depicts a day when there's been overnight rainfall. And down the bottom we have the local time, and up the side we've basically got altitude. And what you can see here is that we've got, along the bottom, we've got this thing called a stable boundary layer. That's the nocturnal boundary layer I was talking about, due to the long wave radiation cooling the surface, and then therefore cooling by conduction the air a very thin layer of air above it. But in the morning, 8 o'clock or something, when the sun starts to come up, we start to get all these thermals building, pushing up that entrainment layer I was talking about earlier. And by midday here, maybe I've done a bit of an exaggeration, but midday here we've still only got like 2 grand. The tops of thermaling height would be like 2 grand or less. So rubbish. We even might have quite a bit of cloud forming at about 2 grand due to all that moisture. And in fact that often happens even when we get to a decent cloud base. We can often have far too much cloud up near the cloud layer due to the amount of moisture that was on the ground a couple of hours earlier. In the evening we get the same sort of thing that we normally get in an evening, where it suddenly cuts off around sort of 6 o'clock normally in this country, where thermals just get too weak, and of course the long wave radiation starts to outgun the incoming shortwave radiation, and they swap, and all of a sudden we've got this quite a stable boundary layer forming again on the surface. And up here we'd expect by middle of the day to have nice cumulus, but don't forget, when we've had overnight rain we often get like things like spread out and excess cloud, which sometimes works in cycles. So sometimes you get an excessive cloud form, spread out and everything, and then that shuts off some of the energy getting through to the surface, and then that cloud evaporates, and then suddenly there's a whole load of sun getting to the surface again, and we get a lot of moist air getting up to the cloud layer again and making it all shut down. So sometimes we get cycles like that when it's been wet overnight. Right, here's a more normal day, or just a different diurnal cycle chart, showing the same thing really, with the boundary layer, and a more normal XC day I'd say here, where it's starting quite a lot earlier, so we can see how like 8 or 9 o'clock we're starting to get thermals. You know, as long as the soil is fairly dry and we haven't had any really dense nocturnal boundary layer or any too much fog in the valleys, we'll get a more sort of traditional start, and by midday we've normally got cloud base up near sort of 4 grand or something, and this whole much bigger window to fly further on an XC day. So we've got, you know, from sort of 11:30 or something we could be away from the hill, and or even 11, and then not land till sort of like gone 6. We've got a lovely nice big window, and I've just shown here all the different, a kind of a very basic form of skew T, just to show roughly what you're expecting in the first one. Like you've just got, obviously it's the coldest air it's at the bottom, and then sort of in the second skew T we've got, you can see how the boundary layer, I don't know if you can see the grey on your screen, but the grey shows the boundary layer growing in thickness, and then by the third image cross section, this is a good day by then. This is a good XE day. Notice the inversion, the capping inversion sometimes gets quite severe, just, you know, where clouds stop, the top of the clouds, cloud top, which just limits any further development of the clouds. It's almost like an ideal day for XE is actually when we've got quite a strong capping inversion to limit the vertical development of cloud. We don't want much of that. We just want little cumulus regularly popping up for an ideal day. The final section is actually just before it all shuts off. You've normally got sort of quite decent clouds and probably the thickest boundary layer, convective boundary layer of the whole day. And then as the stable nocturnal boundary layer sort of kicks in, there remains a kind of a stable residual layer that was formed during the convective phase of the middle of the day that roughly keeps its same temperature profile. It doesn't change much because it's not in contact with anything, so it's not going any energy in it, but it's definitely warmer. It's about the same temperature it was during the middle of the day. But I'm sure that now I've overstayed my welcome and I've talked for longer than I intended to, and I did go slightly off track. I'm sorry, but I hope all this is really useful to you, understanding the weather just a bit better, and I hope I haven't bored you or blinded you too much with technical stuff, but given you little pieces that you can go away with, and I'll definitely leave you with some resources and links somehow that you can go away and do your own studying and challenge me. I'd very much like it if we could have some sort of forum for discussion on this, suggestions for how we could explain this more clearly to people that want to know. and to chat about it and enjoy this amazing thing that we experience every day of our lives and often don't notice it, or at least at worst take it for granted. So thanks for listening. Over and out.